Hi, everyone. Welcome and thank you for joining us. My name is Carmina. I'm your moderator for today's event. We have about 50 minutes of great content prepared for you with 10 minutes for questions at the end. Murthy, the floor is now yours.
Thank you very much for the nice introduction of the logistics. We have a very short agenda here, but we will cover a lot of details. First, we will start with the background of phased arrays and the concept of a phased array, and we will very quickly identify the challenges in designing a phased array. We will discuss briefly about the traditional approach that has been followed for a long time in designing and developing the phased arrays. Then we move on to introducing a modern method that has been enabled by modern simulation and modeling tools. We will also discuss how these modern simulation and modeling tools have evolved in relation to the design requirements of the phased arrays. What are phased arrays? Before we define a phased array, let's define an antenna itself. An antenna is a metallic structure that radiates in desired direction or directions, typically not intelligent. What we mean by intelligent here is that if we want to change the direction of the radiation, we have to physically rotate the antenna. We can form an array of antennas by arranging them in a specific geometry, either 2D or 3D geometries. A phased array is an antenna array plus an intelligence imparted to it. Sometimes we also call these array antennas as smart antennas. How can simply arranging an antennas in a geometry become intelligent? This can be explained by just basic physics of wave propagation. There are two simple equations as shown here. One is the time delay between the elements. The other one is the phase difference between elements. In either of these equations, if we produce a time delay progression or a phase progression at the antenna elements, we can direct the energy to radiate in a specific direction as shown here. Now, if we want to change this direction, theta, we can change the phi or the tau, and we can steer the beam by simply changing the tau or the phi. These animations are from Wikipedia, and thanks to Wikipedia for these animations on their web page. So we have seen that by grouping a set of antennas and then imparting intelligence, we can achieve very interesting functionality. That sounds easy because the two equations are very simple that we have seen just now. But then what is the challenge? As the energy is reinforced in a specific direction, the energy is also reinforced in other directions as well. That is again governed by these same equations. And these are called side lobes and back lobes in which in the other directions where energy is focused in addition to the main direction. These side lobes and back lobes are detrimental to the operation of phased array systems. Obviously, we have to control the side lobes for useful phased array operation, and then that is a big part of phased array design. This can be done by distributing the amplitudes in addition to the phase at the antennas. By precisely maintaining amplitude and phase distribution at the antennas, we can reduce the side lobes as shown in the picture here. As we have seen, focusing the energy in a specific direction is pretty interesting. But it is even more interesting if we can not focus energy in a specific direction, if we can create zero gain into a specific direction for the phased array. And if it can be done in a controlled fashion, that's even better. Can it be done? Yes, it can all be done by creating phase and amplitude distributions at the antennas. We can make the waves interfere destructively in the far field. This is called null steering, and it is a big part of phased array design. Again, The requirement here is that we have to maintain precise amplitude and phase distributions at the antenna array. So it will be interesting to see this precise amplitude and phase distribution that we want to maintain at the antenna is prevented by something. In order to produce this phase and amplitude distribution at the antenna, we are going to employ some sort of a front-end electronics. And these are actually multi-channel front-end electronics. So all these electronics will have parts as shown here, and then all of them will have non-ideal behavior. When they have non-ideal behavior, they're going to disturb the phase and amplitude distribution that we intended them to deliver to the antennas. Because this is a multi-channel system, phased arrays are always multi-channel systems, the parts in various channels will have a different behavior. They slightly deviate from each other in each channel. So that statistical variation also needs to be considered, and that is also responsible for this precise phase and amplitude distribution that we want to impart to the antenna. Finally, the phase shifters and the programmable phase shifters and programmable attenuators are, they have finite states because of the digital control, and then they can only offer finite phase or amplitude values. So that creates what we call quantization error, and then this quantization errors also prevent maintaining this precise amplitude and phase distribution at the antenna array. Let us look at some typical specifications of a phased array. Even though the phased array specifications can be numerous, we can simplify the specifications into actually specifying the characteristics of the far field pattern. As can be seen here, we can understand the far field pattern in terms of parameters like gain, bandwidth, both horizontal and then vertical, side lobe levels, useful steering range. As we steer the beam away from the bore side, the gain drops, what we call scan loss. So at some point, the scan loss is so much that we cannot use the steering anymore. If we exploit the polarization, then we have to understand the specification for the polarization as well. In order to obtain those far field characteristics, we have some design parameters. Again, these are very simple design parameters, the fundamental design parameters. And by starting with these design parameters, we can arrive at a far field very quickly. If there are no impairments in the front-end electronics, all that we have to do is use these design parameters and then obtain a far field pattern very quickly. That is what usually is done in the legacy techniques, legacy methods that have been followed till date. The method starts with simple behavioral models with ideal characteristics or highly approximated characteristics. And then the simple design parameters are used, and then the simple equations are used to arrive at a first cut design. But then a prototype is built and then tested in the chamber. Obviously, one will find that in the chamber, the desired performance is not obtained because the design itself is approximate to begin with. So one has to fix the parts, or sometimes one has to fix the topology itself. For example, should I use a 128 element array or 256 or 512? Should I use a circular one or a hexagonal or triangular or rectangular array, etc.? If we can't get the performance in the anechoic chamber, then we have to fix it, come back with a new prototype, and then test it again until the performance is obtained. This process continues. What is wrong with it? There is probably nothing wrong with it. Phased arrays have been built like this for a long time. They are simply inefficient. And with the commercialization of the phased arrays in the last 3 to 4 years, mainly because of the 5G technologies and also, of course, the satellite communications moving into higher frequencies with phased arrays becoming a must, one has to change the methodology itself. What are the consequences of following the traditional legacy methods? The lack of confidence in the design leads to project proposals that probably are over-designed to begin with. So the price is very high. Probably it did not matter because the phased arrays were deemed as specialty products. But with the commercialization, that's not the case anymore. On the other side, if we are very optimistic about the design, then we run into the risk of not meeting the specs in the course of the project. So we have to indulge in multiple iterations, longer development times, and then probably cost overruns of the project. So as we said, we have to change the methodology. In the new modern method, we do everything in simulation. We arrive at a topology that satisfies, and we start with very good models to begin with. And then we verify the topology by exploring the entire scope of requirements, entire design space. And gradually we increase the fidelity and the accuracy of the models of the parts that we have used and keep verifying the topology still holds. If required, we can change the topology at this point. When the confidence is very high, we move on to building the prototype hardware. At this point, we only have to do a little bit fine-tuning to the design to satisfy the specifications. The modern methods call for modern simulators. From the above design methodology that we just discussed, we can clearly identify that we have to explore the space, design space thoroughly. So, and then quickly, of course. So we need a simulator that runs very quickly. We have to bring high fidelity models into the simulation. And finally, the simulator should be able to predict the real world behavior, especially with the distributed components at the higher frequencies like millimeter waves. So what prevents from this extensive exploration of phased arrays? What we mean by extensive exploration is that the phased arrays are used to steer the beam, so we have to study the performance of the phased array in all the steering angles that it is designed for. Or similarly, we have to explore for all the adaptive nulling that it is designed for. In addition, if some elements are failing, whether the phased array is still functional or not, so we have to fail the elements for each direction and then see if the far field pattern is good enough or not. Let us see what happens if we explore this with the traditional methods and then traditional RF simulators, even though those RF simulators are very good to begin with. If we take an example of 256 element phased array, we have 256 RF channels to analyze for every single direction. Let us say we take about X seconds for one direction of to compute the far field for one direction. Now, if we want to explore in an azimuth range of 0 to 60 degrees and elevation range of 0 to 30 degrees with a resolution of 1 degree, and if we say for each direction we will fail 10% of the antenna elements, and we will do some 10 times, 10 Monte Carlo simulations every time, then we are looking at a simulation time of about 18,000 X seconds. As I said, a very good RF simulator on hand probably can very fast simulation of 256 RF channels can be done in about 90 seconds. Then we are looking at 450 hours of simulation. This is a huge time to see how the phased array is functioning for one exploration. Now, if you have another parameter on top of this, you have to do another 450 hours of simulation. So this can very quickly become a limiting factor. So we really need a very good and very fast simulator for phased array exploration. While we not only need a very fast simulator to be efficient, we also need a very easy to use, very easy to set up the phased array schematics, the phased array system. In addition to this, of course, we need the accuracy to explore. Exploring approximately will only take us to only that much far into the design. So we need ease of use, speed, and accuracy. What we mean by ease of use here, especially, is that because this is a multi-channel system, we should be able to model with the fewer number of parts very quickly and into a desired geometry like a linear array or a rectangular array, circular array, etc., with a few clicks of a mouse. And also, it is possible for phased arrays that we create a small footprint of library and then use that to create almost 80 to 90% of variety of different types of phased arrays. So as shown here, we have a very easy to use library, a footprint of models that can be very quickly assembled to create a 256 element array as shown here. We'll see this in actual demo.
As I mentioned earlier, we have a very small footprint of phased array building blocks here. We just have to place them on the schematic to construct a design that can be set up for any kind of geometry and then any size of the array. Then we have the programmable attenuator, phase shifter, and then a splitter or combiner here, finally running into a receiver port. Let us set up a 256 element array in a rectangular geometry, and then let us look at only the upper hemisphere for now. All the elements in this array are isotropic. We have not yet defined a window for the attenuator, and then we are looking at the bore site 0, 0 here, and then we are going to combine all the 16 by 16 channels in the combiner before they go into the receiver port. In the analysis, we are defining the design one, and then we can calculate we have calculated, and then if you look at the simulation speed, it's only about 0.4 seconds. And then if we look at the data that is collected into a data set, we have the directivity pattern here. We can readily make a 3D plot of the directivity pattern. As you can see, it's a 256 element far field pattern that's plotted. The gain is 29 dB roughly there, and then you can make measurements by placing markers on the graphs, and then all those nice features are there. In addition, there are other things calculated like the G over T and the directivity at the maximum radiation, etc. And then in addition, there is a lot of other details are calculated in addition to just simply calculating the far field pattern. So this is a very complete analysis, but simulated in a very quick time. If we want to apply the windowing, it's very easy. We can just go and then apply, say, a Taylor window with a very low side lobes. We want to get, let's say, 40 dB side lobes, and then if we run this analysis again and look at the plot, we can see that the side lobes are reduced dramatically, they are in the range of about 40 dB down from the peak. So that is how we control the side lobes. One more aspect before we leave the demo. What if I increase the size of this array to an arbitrarily very high size, let's say 10,000 element array? What happens to the simulation speed? So we can see very quickly and run the analysis. The analysis is done now in about 1.4 seconds. So it went from 0.4 to 1.4 seconds, and it gave the directivity pattern plot here as can be expected from a 10,000 element array. We have a very sharp beam as shown here. So this shows that we have a powerful, easy to set up simulator in our back pocket that we can use to explore the array that we are going.
As we have seen in the demo, we could very quickly simulate, and the total time that we need to simulate is only 1.9 hours now with the modern simulator, as compared to the conventional simulator, which was taking 450 hours. So this is a marked improvement, and then this immediately gives a very important tool in our hands to explore the design space very quickly and by setting up very easily, and also with accuracy, which we will talk in the next several slides. So one question that we need to ask is it true only for the 256 elements? Is that the limit? The answer is not. We explored further, and then as we increased the number of elements to 512 and then beyond, the simulation speed became very slow. It was taking much longer time for the conventional RF simulators, whereas the modern phased array simulator is very flat, as shown in the blue curve here in the graph. Even for a 10,000 element array, we found that it takes only a few seconds to simulate for a specific direction. Now, the speed, since we have got the speed in our hands, we can extensively explore the design space. So let us see what are all the things that we should explore and then we can explore. The first one is the geometry. So variety of different types of geometries of phased arrays can be formed, and we can explore them as we have already talked about it. The size of the array. So the number of elements can be changed on the fly. The size, the spacing between each element can also be adjusted very quickly, and we can explore. We can see the far field pattern by changing the size. By adjusting the amplitude distribution by following a windowing, what we call taper of amplitudes at the antenna elements, we can control the side lobes, and then we can very quickly experiment with the different types of tapers to control the side lobes. We can easily scan the direction and see the scan loss, the acceptable range of scanning angles. We can substitute different types of elements very quickly. The patterns can come from either a simulated electromagnetic tool or from measurements of the actual element. We can bring those patterns and then simulate in this simulator. We can also define the polarization. So we can have each location of the antenna, we can have dual polarized antennas, and we can study the effect of the non-ideal polarization between the two orthogonal polarizations, like vertical and horizontal, or right circular and then left circular, etc. We can also study the quantization effects of the programmable phase shifters and the attenuators. We can, more importantly, study the failure of the antenna elements. If certain number of antenna elements are failing, what will be the impact on the far field pattern, and ultimately what will be the impact on the phased array system itself. Sometimes we may have to follow both time progression and then phase progression in a design to obtain, for example, for broadband systems, we can initially do a coarse time delay method followed by a fine phase difference method so that the implementation of the phased array becomes more practical. So multi-level architectures can be easily studied. As we can see here, we can do a number of variety of experiments to extensively explore the design space. Increasing the accuracy. How can we increase the accuracy of the models? First of all, higher accuracy comes from models that actually behave like a hardware. For example, here, as shown here on the left-hand side picture is the amplifier model icon. It should behave like the amplifier actually in the lab. So that we should capture the behavior of the amplifier under varying frequency conditions, under biasing conditions, under load conditions, under temperatures. We can capture that and then put it into the tool. Now, the simulator itself should be able to capable of producing the effects, the real-world effects that are only possible in the hardware usually. So, for example, the simulator should behave like an instrument measuring the device. So the simulator here simulates the amplifier above, and it should produce the same effects like an instrument measuring the hardware in the lab. So how can we increase the accuracy of the models itself? The best thing to do is, if we have the measured data, we can just simply bring the measured data into the simulation and then create models. So the measurement-based models are the ultimate models with the highest accuracy. We can also bring in the element patterns from electromagnetic simulation, and we can also bring the S parameters or the reflection coefficients of all these elements, and then in the simulator we can put them, and the simulator can actually then take into account the coupling between them, and then it can produce effects that typically happen in the hardware world. Phased arrays exhibit a unique behavior, and we call that active impedance or scanning impedance. One peculiar characteristic of phased array is that as we scan the beam, the impedance looking into each one of these elements changes. This changing beam impedance or the changing element impedance will impact the performance of the amplifier if the amplifier model can behave based on the load to which it is connected. And then we have one such model called X parameter file if connected with varying load impedances. We also are showing here the programmable attenuator and then the programmable phase shifter supplied and then modeled with the S parameters for each one of the states. Now, if we have this kind of accurate models for the parts, can the simulator exhibit the behavior of scanning impedance, that is the changing impedance with scanning angle? Let us see. In this graph, we are looking at the real part and imaginary part of the impedance, looking into each one of the antenna elements. The antenna element number is shown on the x-axis, and the y-axis on both left and right represent the impedances, real and imaginary parts. As we can see here, we are measuring this impedance at each element for a beam angle of theta equals to 0 and phi equals to 0. In this graph, we are looking at the real and imaginary impedances of each element for an elevation angle of 15 degrees. As we can see, this is quite different from the previous 0 degrees elevation angle. We change the angle to 30 degrees elevation, and again we can see that the impedance profile changed quite significantly. So we have seen at 3 different angles the impedance changing quite very well, quite significantly. So we have to actually, in practice, have to simulate, we have to collect the variation of the scanning impedance or all scan angles that we are interested in, and then we can derive statistically how much variation is happening, and then we can go back and then redesign or design the impedance matching networks between power amplifiers connected to each one of the array elements. Another interesting and important phenomenon that happens in phased arrays to do with the non-linearity of the front-end electronics that is connected to the phased array. As the signals pass through the nonlinear devices or the nonlinear components, they produce additional frequencies, undesired additional frequencies. When these undesired additional frequencies reach the phased array antenna, they also get radiated, even though not very efficiently, but they do get radiated. So, but the phased array itself is designed for a specific frequency or frequencies. So what happens to all these additional spurious products that arrive at the phased array antenna? The only way to know about them is actually to go to the anechoic chamber and then make a measurement at each one of these frequencies, understand their far field pattern. This has been the traditional approach. As shown on the left side, we have an anechoic chamber where our phased array is the device under test, and there is a standard horn antenna that is radiating the signal, and we rotate the antenna or the device to collect the far field pattern at the various angles. So when we do this, we do this at 10 gigahertz because that is the desired signal, but we also have to do for all other frequencies that are generated because of the nonlinearity. So this all can take a long time, typically a few days to several days, maybe a week, depending on how many frequencies, how many times we have to calibrate the chamber, all those the effort that is required. Now, in a simulation, we can do this whole thing probably in minutes and hours without leaving the desk. We can do it on everything on the computer, and then we can plot all of them, and we can see the direction in which these beams are going. So this phenomenon has to be produced, has to be predicted by the simulator very accurately. That's what we are looking for. We can plot the same 3D overlaid plot shown in the previous slide into a much more useful, more intuitive 2D plot as shown here. What we have done is we have taken in the 3D plot the tip of maximum value of each frequency there, and then plotting that frequency here, and then the marker, if we hover there, and then we can find that that particular frequency, the value of the far field EIRP value of that frequency, and the direction in which that maximum value is happening. So we are showing all the useful information in a 2D plot here, because what we are interested in is what is the maximum value of that spurious frequency that is getting radiated. If we reduce that maximum value, naturally the far field pattern will reduce, and then we probably eliminate the radiation or reduce the radiation of the spurious frequency. And also another important thing is here we can show all the frequencies very clearly, and then very visible to our eyes in a 2D plot. Another useful graph that we can plot is a phi cut plot. What we mean by that is that we are cutting the 3D graph in a specific angle, and then we are plotting each one of those frequencies that we have seen in the 3D plot. By doing this, what we are able to achieve is now we can impose a mask as mandated by the standards bodies or the regulatory bodies, and we can see that nothing is violating the mask. So we can clearly see here is that 8 gigahertz intermodulation, unwanted, spurious product is violating the mask. So we can, since we identified, we can actually fix this, hopefully, in a simulation itself. If we were to notice this in an anechoic chamber while everything is designed and then developed and then prototype measurement is done, we have to go back and then fix the hardware and then come back to the anechoic chamber to verify that again. We identified that 8 gigahertz intermod was violating the mask. Now, one solution to fix this problem is to modify the filter after the amplifier before the signal, before the spectrum is entering the phased array front-end electronics itself. So what we have done here is that the filter was initially going from 9.2 to 10.8, a slightly wider opening of the filter. We modified that to 9.5 to 10.5. So we tightened the filter a little bit, and then we can clearly see that when we resimulated that and then plotted the phi-cut plot again, all the spurious products have gone well below the emissions mask, the spectral emission mask that is mandated here. We can do other types of very interesting simulations, which is almost like modeling the anechoic chamber and all the front-end electronics in simulation itself. What we are seeing here is, if you just focus on the headings of the blocks, we have a 5G new radio downlink source that is going through some front-end electronics. And we are steering the beam. We created the weights, the phase and amplitude weights that programmed the phase shifter and then the attenuator. And finally, we amplified the signal through a power amplifier and passed it through a very well modeled channel, line of sight model with angle of departure and then angle of arrival information. And finally, we added the noise that is added to the signal as it goes through the environment. And then we made the EVM measurement at the end of that. So this is an EVM measurement in the far field because we radiated and then we are measuring the EVM in the far field. We can also measure things like the secondary synchronization broadcast, SSB signals, etc., into the far field and then as shown here. This plot is a very important plot. In simulation, it can be obtained very quickly, whereas in a measurement, it will take days at least to make such measurements. And then what we are showing here is as we moved in away from the phased array, initially we might be in the near field. As we move into the far field, how the EVM pattern evolves. So at the bore site, at the 45 degrees, we have the best EVM, and then as we move away from that, the EVM degrades as shown here. So far, we have seen that with proper tools, we can meet the design requirements, and we can gain a lot of confidence in our design itself. So let us conclude what we have found. We found that the design requirement for phased array is that we have to explore the design space thoroughly. This can be a very long simulation exercise, and because of that long simulation time, probably in the past, a thorough exploration was out of bounds. People did not consider that. But that actually has put a requirement for the modern simulator, and then modern simulators have come meeting that requirement. So we now have a very fast simulator for phased arrays on hand, so we can explore the design space very thoroughly. The next requirement is that the building blocks that we model in simulation have to be very high fidelity. If we explore a design that is approximate, it's not going to be very useful. So we have to explore, not only explore, we have to explore a design that is very accurate. So we might be able to go and then make very good measurements and then bring that data as high fidelity models, but the simulator should be able to absorb that. The simulator should be able to absorb it and then quickly parse the data and then simulate quickly. So that put another onus on the simulator requirement, is to be able to understand these high fidelity models and then simulate very quickly. The third one is that we need the phased arrays are very complex systems, and we need to be able to, they produce very peculiar phenomenon like scanning impedance and then in the radiating spurious frequencies in different directions, and it does all sorts of things. So the phased array behavior in the real world is pretty different from many other electronic systems that we deal with. And the simulator should be able to predict this behavior and then produce that behavior in the simulation for us to be able to understand that and fix it in the simulation itself. So the simulator should be able to, behave like a real-world measurement instrument. We have seen that the simulator has come a long way, and then the simulator is able to now predict the real-world behavior. We have seen the active impedance. We have seen the spurious emissions in different directions, and we have also seen the measurement of EVM in a far field with a probe. So these are all very good for a modern simulator, and then now we have them on hand. We have some additional resources for you. You can visit any of the links here to understand a little bit more about SystemVue. And the last link shown here under the downloads is where you can download SystemVue software itself and apply for a trial license. You can also see some more additional how-to videos on SystemVue, and these videos are not just for SystemVue, but other areas of our simulation and modeling software, and then the device modeling software, etc. And then, of course, you can also find very specific to phased arrays, some of the videos quoted here. You can visit them. And finally, don't forget, you can get a 45-day evaluation copy if you download and then apply for a trial license today.
Now it's time for the question and answer session. Okay, Murthy, here's your first question from Matt. Can I use my own windowing function?
Yes, you can certainly use your own windowing function. What I assume when you say windowing function is you want to achieve a specific amplitude distribution by programming the programmable attenuator. You can do this by going into the programmable attenuator properties window and choose the property for windowing as custom window. Then it will let you enter your own custom window there.
Great. And here's a question from Russ. Adaptive null steering is a very important functionality. I want to incorporate my own algorithms. How can I do it?
Very good question. You can bring your algorithm, whether it is in the form of a C++ code or MATLAB or HDL. You will be able to bring that code into SystemVue as a model, and when you simulate, you can actually put breakpoints in your code, and you can debug as the simulation goes on. You can debug the variables in your code and then modify it, correct it, enhance it, or fix anything that's not working. So SystemVue is very conducive to bringing your own algorithms.
Great. And here's a question from Xiao. I want to model the impairments of the parts like amplifiers across all the channels independently. Can I do it?
Fantastic question. We can do this to a limited extent today, but in the current release, this is being addressed pretty actively. So you will be able to see at the end of the release in next few to several months, you'll be able to address the parameters on the amplifiers in various channels. It should be possible in future.
Okay, very good. And here is your question. Let's see. Let me get this next question. And this question comes from Taylor. The TR models I want to use in my phased array system are in the form of an integrated circuit. How can I bring the model of the IC into SystemVue?
Well, there are multiple ways to do this. In case you have your integrated circuit already in the form of a hardware, or it is in some sort of a simulator. You can bring in characteristics like the S parameters, noise figure, 1 dB compression point, etc., and then model that into SystemVue as a template in SystemVue. Or you can extract, in case this integrated circuit exists in advanced design system, you can extract an X parameter model for that under various conditions, and you will be able to bring X parameter model directly into SystemVue. And the third option you also have is, again, if your integrated circuit is in either Cadence environment or in ADS environment, there is a simulator called Golden Gate, and if you use Golden Gate, you will be able to extract what we call fast circuit envelope model. And then again, you can bring that fast circuit envelope model into SystemVue and then simulate it. As you bring the model as a matrix model, it will replicate itself to the size of the phased array. So it's pretty neat.
Very good. And your next question comes from Frederick. I have a very large array of few thousand elements. Is it possible for me to simulate that entire array to capture the S parameters of the entire array? How can I still account for scanning impedance meaningfully?
Yeah, this is a very typical flow for very large phased arrays. You won't be able to simulate the entire array and capture the S parameters. That's too much for any electromagnetic simulator, any physical simulator. So what you do is you can use what we call periodic boundary conditions in the EM tool and get the pattern. At the same time, you can choose, because it's infinite, your array is very large, you can neglect the edge effects and you can choose some central element as your unit cell and then bring the pattern of the unit cell into SystemVue. And there are also standard equations that will allow you to compute the active reflection coefficient or the reflection coefficient of the array with respect to that can be computed from the unit cell pattern, and these can be input into SystemVue, and then from there onward, SystemVue takes care of predicting the active impedance that we have seen in the simulation, in the presentation.
Great, thanks. Here is your next question. This comes from Monty. For the programmable phase shifter, I have multiple S parameter files corresponding to the phase states of the phase shifter. Can I use them?
Absolutely, yeah. In fact, we have very briefly covered this in slide number 24, if you remember. So what we have shown is we had a phase shifter from Analog Devices. They published their data in a data sheet, which was a 4-bit phase shifter. So we had 16 different S parameter files, and we were able to bring all 16. And one of the neat things about the phased array design kit is that you don't have to enter the names of all the 16 S parameter files. If you name them sequentially with the numbers, and you will be able to just to specify the first file, and the simulator knows that it has to look for the rest of the 15, and then it will read all the other 15 from your directory.
Okay, thanks. And here's your next question from Andrea. Can I fail a certain percentage of antenna elements in a random fashion and simulate the far field pattern?
Absolutely. This is one of the key functionalities of a phased array design, and SystemVue certainly does that. You can initially you can start. We start in SystemVue as all elements being active and then functioning. And from there onwards, we can fail a certain percentage, say 10% of the elements, and we can perform simulations. And then we can progressively keep changing these, randomly changing these percentage of elements, and then we can keep computing the far field pattern. It's not just the far field pattern. You can compute anything else, like very useful parameters like the EVM in the far field or the AIRP in the far field, etc. You can compute, and you can see if the array is functioning satisfactorily or not.
Okay, great. And here's a question from Yarrow. I need to design a broadband phased array. Can I use your tool SystemVue to do that?
Yes. We did not cover too much on this, but in the slide where I said all the parameters that you can explore, I briefly mentioned about the multi-level design of phased array. So what we do here is we can use the time delay equation that I showed you on slide number 5, which is a very simple equation, and you can distribute the time delay across the array elements, and you can achieve a beam direction that is independent of frequency. But then the issue with this approach is that if you have a large array and the elements are closely spaced, then the time delay that you have to maintain between elements is very tiny, and maintaining that very tiny time delay difference across the entire array is rather difficult and also is expensive. So in those cases, what we do is we divide the array in a very coarse fashion into a subarray, let us call it that way, and then we apply the time delays. To give you an example, let's say we have 64 element phased array. We can initially divide this into a 2 by 2, 16 elements per quadrant. So a 2 by 2 matrix, and you can apply time delays across all the 2 by 2. Now you can clearly see that the distance between the centers of each one of these quadrants is quite large, and your time delays are big. So you will be able to maintain very accurate time delays. Thereafter, we divide each one of those quadrants into 16 elements, and then we can apply phase shift methods for all the entire 64 elements, and then achieve the beam direction. So we are doing a multi-level, here 2-level design, and then this allows reduces the burden of maintaining very precise time delays, but at the same time it gives us the ability of broadband beam. But of course, one small thing to note is that it's not going to be entirely frequency independent, but the frequency dependence will be tremendously reduced compared to just the phase shift techniques that we use.
Okay, great. And really, this will be your last question. This comes from Frank. Can I do simultaneous multiple beam formation?
Yes, it can be done. In fact, we have an example, or maybe more than one examples in SystemVue product. If you would like to try the product, you can access the example, and then please let us know if you need any help. This can be readily done in SystemVue.
Okay, great. And Murthy, thank you so much again for your presentation today. Thank you for attending today's webinar brought to you by Keysight Technologies. Join us next month for the continuation of our Engineering Education webinar series, and enjoy your day.